All right, so, well, 2 days ago, since yesterday we had a nice day off, 2 days ago we talked all about vectors, introduction to vectors, and we did adding vectors and multiplying by a scalar. But the tricky part is, like, we don't really have a good way of talking about vectors. We don't have a good number system by it. You can draw a vector, and the size of the length of the line represents the magnitude, and then the actual direction of the arrow represents the direction of the vector, because again, vectors are made up of two components. But without that, but that's not a great way of doing things. I mean, can you imagine doing a bunch of complex math and drawing arrows all over your page to represent vectors and measuring them with a ruler to determine their magnitude and that kind of stuff? Like, it's not a very good way of doing things, right? So it's nice if we have a number system by which we can actually talk about vectors in a more meaningful way. And that's where Cartesian vectors comes in. So a lot of what we do for the rest of this course, for the rest of all the vector stuff, will be working with Cartesian vectors. We will still occasionally go back to non-Cartesian vectors, and you're given the magnitude. But how would you be given the direction? I mean, north, we don't really do that. We will do it in a different way. We'll talk about that a bit. I think we'll talk about it tomorrow, but like, it's not as useful and not as informative. So a lot of vector math happens in the Cartesian plane or some other kind of plane that has a number system. And it tends to work very, very well. So we'll start. So I hope that you spent some time thinking about vectors and working with vectors, like doing the work independently, because that's when you start to force yourself to really think about these concepts. Because like I said, it seems simple, but some people who were in yesterday and asking questions, like, there's clear misunderstandings and there's reminders that have to be made throughout about one of them, that a vector doesn't exist in a particular position. When you're staring at a vector that's been drawn somewhere, you think it exists there. But you can pick vectors up and put them wherever you want if it's appropriate. So you got to remember that. So there's a lot of these little things. And again, today there's some big ideas, but there's a whole ton of little things. And that can just get overwhelming, and you think it's easy, but then all of a sudden on a test you're asked to do something, you're like, well, I don't actually know what this is asking. Computationally, it's very easy. You got to know what it's actually asking you to do. We're going to start, though, with the definition of a vector in the Cartesian plane. And that is a vector with its tail on 0, 0, and its tip on point AB. So these are both points. We denote that vector with square brackets and the same coordinates as the point AB. So I'm going to go ahead and draw this. So it starts on the origin and it goes to some place like this. And I'll call this vector u. And this distance is a, the x value. And this distance is b, the y value of that point. Tip is at the tail is at the origin. Tip is at the point A and B. So vector u equals a, b. It's a nice notation. It's so powerful. Now we have a good, clear, straightforward number system by which we can start doing the things that we do with vectors. Easy enough? Interestingly, I kind of thought that, like this, there are different standards of writing out vectors. And I kind of thought this was maybe the high school version because you can write it on one line of paper and that's nice. But I was under the impression that, typically speaking, so if you take linear algebra in university, this is where vectors leads into linear algebra. Okay, but the way we do it isn't really linear algebra yet. It's just learning about vectors. But I was under the impression that when you did linear algebra, you kind of wrote vectors like that. and that this was the standard way of doing it. But I've since heard that actually some professors in university still write them out horizontally, but a lot do it vertically. Some textbooks do it one way, some textbooks do it the other way. So there's no like clear convention on how you write vectors. It's not even clear, and this is the worst part, that you use square brackets. There are people who do it like this. But what's the problem with that? I mean, my goodness, what a terrible, to me, way of doing things, because like how can you differentiate that between a point? So you would have to use some other notation system to show that this one's a vector. Otherwise, you would think it's a point. At least if we use square brackets, we know when something is a vector and when something is a point. So that's how we're going to do it for this course. But be aware that your profs next year, if you take a course that has anything to do with vectors, may do it differently. And this is a very common way of doing it. Okay. And then the other reminder is vectors don't exist in a particular position. So the vector u, which is AB, is not just this vector. It's also, let's say, this vector. This is also vector u, as long as this distance is b, from whatever that value is to that value is equal to this distance, because this was from 0 to b, so it's obviously distance b. And this distance has to be a. As long as those distances are the same, those vectors are equivalent, they're the same vector. So we're not saying all vectors start at the origin. We're not saying if you're talking about a vector, it's definitely at the origin. You can still move vectors around in Cartesian space. Okay. Another little definition here, unit vectors. The unit vectors is different from a unit vector. The unit vectors are these funny little things that we actually call I hat and j hat. That's what we call them. Okay? And they are literally written out like that. So I hat is written, and it's hard not to dot your I, and if you dot it, it's fine. But like then you actually draw a hat on it. Don't change the hat. It's not a top hat or a baseball cap or something. Like, no creativity in mathematics. Okay, so I hat and j hat are drawn like that. And they are perpendicular to each other, is what this means. And they are, by definition, I hat and j hat along the positive x and y axes. And a unit vector means magnitude of 1. So there are other unit vectors that point in all directions, but I hat and j hat are special ones. And they're alphabetical. So x then y, I then j. I is the one along the x-axis, j is the one along the y-axis. And if they're going to be unit vectors, we talked about magnitude. We're going to talk about it more today in terms of Cartesian vectors. That means I hat is 1, 0. That will give it a magnitude of 1. And it'll be on the x-axis. And j hat is 0, 1. Now, these are very important definitions in linear algebra. We don't use them a lot. But it is something that you'll often are asked to do on a quiz or a test or something like that. And so don't forget what it's asking when it's talking about I hat and j hat. Make sure you remember these things. Okay, so I hat would be a vector like this that has length 1. And j hat would be a vector like this. That has also length 1. Okay, so any vector, let's say like vector AB, can be expressed either in terms of the unit vectors, I hat and j hat, or in terms of its horizontal and vertical components. So vector AB in terms of, this is in terms of I hat and j hat. If I were to write it out in terms of its horizontal and vertical components, that's like a times I hat. Now, we haven't even done multiplication yet, but we're going to momentarily. And we haven't done addition yet, but we're going to momentarily. But all of that is quite intuitive. So I think you will accept this. I multiply the unit vector I hat by A and the unit vector j hat by B. And to write it out in its horizontal and vertical components, I could do it like that. Hey, and we're going to see an example of that momentarily, so I'm going to leave it like that. These are the kinds of questions that don't come up that much. It's not something we do a lot of, so you'd be inclined to forget what that even means. But it's so easy. Those of you that have taken physics, you probably can see why somebody might want to have a way of writing things out in terms of the horizontal and vertical components. That's something you do a lot of in physics. Again, not something we're going to do a lot of, but you can see why you might. Okay, good so far? Magnitude. So if u is the vector AB, then the magnitude of u is the square root of a squared plus b squared. Why would that be true? Very good. So let's do a little sketch of this thing. Here's vector u, which is AB, which means this value would have to be A, and this value would have to be B. Again, it doesn't have to exist at the origin, but this is the easiest way of thinking about it. Which means this length is length A, and this length from 0 to B is length B. And so if I think about this as a triangle, it has length A here and length B here, and that's a right triangle. So the length of this line, which is the magnitude of a vector, is its length has to be Pythagorean theorem. So you can memorize that formula. There's a lot of tiny formulas we're going to talk about today, or tiny little properties we're going to talk about today. You're more than welcome to memorize them all. Not the best way of doing things, memorizing things without any clear understanding. But, you know, it's easy enough to memorize that as a formula. But if you understand that it comes from Pythagorean theorem, you don't really have to memorize it. You just make it up. You just redevelop it every time, right? It's Pythagorean theorem. Okay. What about adding Cartesian vectors? Well, it's intuitive. So that's easy. So if vector u is u1, u2, and vector v is v1, v2, vector u plus vector v is u1 plus v1. That's your x component, your horizontal component. And u2 plus v2 is your vertical component. And vector u minus vector v is just u1 minus v1, u2 minus v2. And again, remember, how do we add vectors that are in different directions? We put them tip to tail, and then we see what the resultant vector is. So that's what this would accomplish. And you could visualize that by graphing a couple of them and thinking about it. fact, I'm going to sketch this quickly. I don't think you want to sketch. I think you just want to watch. If this is vector, this will be vector v, and this will be vector u. So if I do u plus v, I take v and I add it on to u, and that's the horizontal component of u plus the horizontal component of v, right? Of course it is. And this is the vertical component of u plus the vertical component of v will take you all the way to the end, which is our resultant vector. So of course it makes sense and it's intuitive. That's what you would do by intuition. That is what you're supposed to do. So that's all easy enough. The stuff that follows our intuition is always easy. It's the stuff that either has no intuition or is opposite or somehow different from our intuition that becomes harder. Okay, so an example here, determine the sum of those two vectors. This is what I mean by a lot of the computational stuff that we do is so easy. Always thinking about what vector addition actually is, or vector subtraction. Remember that from when we talked about it previously, what it actually is and the resultant vector that you get. Because when we start to talk about Cartesian vectors, we don't talk about it that way as much. We just start adding things and that sort of stuff, okay? Okay, multiplying a vector by a scalar. Again, this is very intuitive. I think I mentioned this. What does it mean to multiply two vectors? It doesn't mean anything. But multiplying by a scalar is fine. Okay, so multiplying a vector by a vector is meaningless. It's not defined, so it's totally meaningless. And this is something we're going to talk about starting tomorrow. It'll start to make a lot more sense. But you can multiply a vector by a scalar. We've already talked about that. Okay, so I am going to let vector u, because I don't think it says there. Oh, and I'm going to let it be 1, 2. But it says here, if u is u1, u2, and k is some element of r, so k is our constant, then k times u is just k times u1 and k times u2. So it's a vector, and it's almost like distributive property, you're just multiplying it into each part, right? So then if I'm going to do this example of 3 times u, I get 3 times 1 and 3 times 2. Get out your calculator if you have to, or if you can do that in your head, then that's fine. Okay, but what does this actually look like? So 1, 2. This is u. 3 to 6 goes to there. Collinear. We talked about this yesterday. You multiply by a scalar, they're collinear. Sure looks like it is to me. Why do you think they call them scalars? It scales things up. Think about a scale of a picture. So here, this is actually a little demo of the distributive property I think that we were talking about previously. But you could also just think about this. So this is a and b, and r is a plus b. But if I multiply through by a scalar, look what happens. Like it does just scale it up. That's what this little demo is doing. So I don't know the actual history of why it's called a scalar, but it clearly has something to do with the scale of the diagram, or scale diagrams are scaling things up or scaling things down. You could scale things down as well. Questions so far? Okay, I think we have a few examples to do. So we're given a couple of vectors here, u and v. This is a very common question that you would see on a quiz or a test. Given u and v, do a whole bunch of different things. Or maybe given u, v, and w, or a, b, something like that. Do a whole bunch of different things. Like find an expression for u in terms of its horizontal and vertical components. So if vector u is 3, negative 5. Writing it out in its horizontal components would be 3, 0, plus 0, negative 5. We showed the steps for that previously in terms of A and B. Basically, I'm multiplying it, but you don't have to do this. Like, it's so easy. Why would you do 3 steps to get this done? But basically what you're doing is 3 I hat plus or minus or plus negative 5 times j hat. Sorry, see how easy it is? 3 I hat plus negative 5 j hat. And I hat is 1, 0, and j hat is 0, 1. And when you multiply through, you get this. And if I added this back, I'd get u. Because now we have definitions for adding and subtracting and multiplying by a scalar with vectors. Express u in terms of the unit vectors. So this is like almost backwards, but well, I guess I kind of did it up there, didn't I? So this would be 3 I hat minus 5 j hat. Negative 4 times vector u. Negative 4 times 3. Negative 4 times 5. And visualizing that if I drew these vectors, 3, negative 5 would be down here somewhere. Like if I started there, 3, negative 5. And then negative 12, 20 would be have a much greater magnitude, and it's going the opposite direction because negative 12, 20 would go up this way, right? So 3, negative 5 might be down here, and then negative 12, 20 would be way up here. But those are 2 collinear vectors in opposite directions because of the negative that was out front. Okay, and I don't think you need my help for this one, but now what is vector v again? Negative 2, 4. Nine minus 4, 5. Negative 15 plus 8, negative 7. Easy enough? Still good? How about the magnitude of u? So this is our formula. Who remembers our formula? Good. It's Pythagorean theorem, right? So this is equal to the square root of 3 squared plus negative 5 all squared, 9 plus 25, which I believe is 34. What about the magnitude of vector u minus vector v? How would we find that? Something I said the other day is when you perform operations on vectors, sometimes your result is a scalar, sometimes your result is a vector. And that's really, really important. Okay? You'll see a really clear example of that tomorrow in your practice over the weekend. But I mean, we'll take it for granted on this question, I think. But right away, you could use some of that thinking to answer this question. How would I do this question? Yeah, so when I find u minus v, that's going to give me a new vector. Then go ahead and find the magnitude of that vector. So I'm going to actually do this in 2 steps. You could do it all together. But what is u minus v? Well, it's 3, negative 5 minus negative 2, 4. 3 minus negative 2 is 5. Negative 5 minus 4 is negative 9. And then to find the magnitude of that, it's 25 plus 81, which works out to 106. Everybody okay so far? Okay, another thing that you're often asked to do is determine a vector in the opposite direction. What does that mean? We don't use this term loosely. If you are walking in the opposite direction of your friend might be going off this way and you might be going off that way. But in vectors, this would not be opposite. There's a strict definition of two vectors that are opposite. Opposite direction is a little bit different. So what does opposite direction mean? Anybody remember from our last note? Yes, negative v would work. That would be an opposite vector, a vector opposite to v. Opposite direction just means collinear, but the other way. So still collinear or parallel, but pointing the opposite direction. So we'll visualize this in a second, but negative v would work. So if vector v is negative 2, 4, then opposite would be negative vector v, which would be negative 1 times negative 2, 4, which would be 2, negative 4. But I could also do 4, negative 8. That would be collinear because I'm just scaling it up, but it's still the opposite direction. So what does this look like? Where's negative 2, 4? Negative 2, 4 is here. So some people think, what about 4, negative 2? Where's 4, negative 2? 4, negative 2 is there. Not opposite. So what would be correct? 2, negative 4 will be, or 4 and negative 8, again, you can see would also be opposite direction. Yep.
So basically, like a reflection to the line perpendicular.
You could think of it that way, or yeah, or 180-degree rotation, like rotational symmetry. We talked about that. Yeah. Okay, a unit vector. Oh, this is a tricky one. This is another one where it's actually not that hard, and it's something you could memorize, but a lot of people don't, and then they don't know what it's asking and leave it blank on a test. A unit vector that is collinear with vector u. So if we recall, vector u is 3, negative 5. And we already came up with the magnitude of vector u. I'm going to write this over here, actually. Doesn't really matter, but. If you hadn't found the magnitude, you would have to find it. We already found it. And to do this, we're going to multiply by some k. Some constant. But we skipped this part. We need to talk about what is a unit vector? Not the unit vectors, just a unit vector. What's a unit vector? With a what of 1?
Magnitude.
Right. Any vector with a magnitude of 1 is a unit vector. The unit vectors, capital T, I guess, is I hat and j hat, right? But any unit vector is a vector with a magnitude of 1. And what is collinear? We kind of already talked about that. It's just another way of saying, fancy way of saying parallel that we often use in vectors. Okay, so it could be opposite or it could be in the same direction. U does not have a magnitude of 1. It has a magnitude of root 34. So it turns out, in order to do this, our k value is going to be 1 over the magnitude. Always 1 over the magnitude. So k times u is 1 over root 34 times 3 negative 5, which is 3 over root 34 negative 5 over root 34. But why?
Because because you have a magnitude, if you divide the number, if you divide the magnitude by itself, then you get 1. So what you're doing is you're dividing each of the components by the magnitude, so then the components will equal a magnitude.
Very nice, good description. I think it's it's hard to describe, right? It's hard to explain why, but that was very good. I think doing it and calculating the magnitude would help. So what is the magnitude of KU? Square root of 3 over root 34 all squared plus negative 5 over root 34 all squared. Now, you don't need to know this. You don't need to do this every time. I don't know that it's going to necessarily, I might help you remember what you're supposed to do. In the end, like I said, you need to know what to do. But what does this work out to? Well, 3 squared is 9. Root 34 squared is root 34. It's 34. Negative 5 squared is 25. Root 34 squared is 34. Already have a common denominator. Well, what is 9 plus 25? Well, it's 34, because that's where the 34 came from in the first place, because it came from the magnitude of u. So I end up with the square root of 34 over 34, square root of 1, which is 1. So the magnitude is 1, and it always will be if you divide each of the components by the magnitude of the overall vector. Okay? Again, not something we do a ton of, but an important idea in linear algebra, and it will come up on a test somewhere, so make sure you remember what you're supposed to do. What about a unit vector in the opposite direction to u, but still unit vector? So it's just the negative of this. Okay? So look at all the little things that you need to know how to do. And again, you could scale that up if you want. Oh, no, it said a unit vector, so you can't. So you got to leave that alone. Yeah, so unit vector, so you got to leave that alone. So there's only one unit vector in one direction and one unit vector in the other direction. You can't scale those up or down. All right, last thing we're going to talk about is Cartesian vectors between 2 points. So let P be x1, y1, and Q be x2, y2, and there are 2 points on the plane. So we're going to draw this out. So I'm going to call this P. Now that's not vector P. P's not a vector, P's a point. But I'll call this vector A. And then I'm going to have Q, which this point Q, and I'll call this vector B. If I want to go from P to Q, I'm doing that. But we're supposed to actually find the coordinates of that, like the name of that. Like, what is that actual vector? So all the work that we did previously from the first day, how does that help us with this? We're going to do some thinking here, and then again, there's going to be something that you just have to remember what to do. Somebody tell me, you should be able to figure this out. How do I get from P to Q with the vectors that I've been given? It was like all those diagrams that you were given, the funky shapes and stuff. Zach? It is not. But you're on the right track. But if I went A, that would start here and go here, and then B would go up here. So that doesn't take me from P to Q. So what is it? Not quite, because that would still be A, and then I would go minus B, which would take me somewhere over there. I think that might give me QP if I did it like that. Don't you remember what we did before? Negative A plus B. So I start at P, negative A will take me down to the origin, and then plus B will take me along B to Q. And I've gone from P to Q. So very good. So what that actually is, so PQ is negative A, which is P to, what's this point? O, the origin, right, I think? Usually we call it O. So I go from P to O, and then I add O to Q. Well, doesn't that make sense? This is like the stuff that we saw when we were adding vectors before, and the O's kind of cancel because of the way this question is formatted, the O's cancel. So I can always split a vector like this up into PO plus OQ, right? You could always do that. Or PC plus CQ. Like you could always split it up into however you wanted, as long as it's P something plus the same something Q will always be PQ. We know that? We understand that? But but this isn't A. This is actually negative A. And PO is not a vector that we know what it is. So I got to flip it around because I actually know what the vector OP is. So it's the negative of OP plus OQ. So like I flipped around A, and then I used A, and then I flipped it around again. So it's a little wonky, but don't overthink it. We know that this is PQ, but I can't figure out what the value of PO is, but I do know what, so if I make it negative OP, that's the same as PO. And I'm going to flip this around as well, just because this is how we tend to do it. So in other words, we subtract backwards. This is what you can just kind of remember, but you also have to remember what that means. Because what is vector? Yes?
How do we know which one is under the, like, we said negative OP, but because we knew OP was on top of Q, right?
No. It wouldn't make a difference. No. If you're going from P to Q, you got to start at P. So you're always going to start at that one. But here's the reason why we had to flip this around. What is OQ? Well, it's from 0 to this point. So that vector is just x2, y2, right? This was the definition of Cartesian vectors that we started with. No? Because that's the definition of a vector, is its tail on the origin to that point. Q is point x2, y2. So the vector that goes from the origin to Q is that vector. You just put square brackets instead. Minus OP, which is x1, y1. So this would be x2 minus x1 and y2 minus y1. Subtract backwards. Take your points, turn them into the vector that's associated with those points, starting with its tail on the origin. And if it's going from P to Q, then subtract OQ minus OP. Not hard stuff. You got to remember what to do, but doing it is super easy. Are we okay with this? If you want to come back and think about it, you can. Oh, I was going to do this. So just to highlight that we went that way, and then we went this way. Oh, shoot. To get from P to Q. So what would the magnitude of PQ be? Well, just using our magnitude formula, it would be the horizontal component squared plus the vertical component squared. Oh my gosh. Does anybody see what that is? Look. What is it? Anybody? Anybody? It is the magnitude of PQ. What else is it? Oh, I don't really remember. Back in grade 10, remember the unit you did midpoint of a line segment and medians and altitudes and right bisectors? No? Closest point to a line. And another thing we did was length of a line segment. Very good. This is the formula for length of a line segment from back in grade 10. For the exact same reason why it's the formula for this. Like if you went, don't worry about it. You haven't done it since grade 10, so I'm not surprised you don't remember it. But it's something you did back in grade 10, in the very last unit of the course probably. And it's the same formula for the same reason. The rationale behind it would be exactly the same. Anyway, okay, so let's use this once. So we're given a couple of values. Find the position vector and its magnitude. So vector AB will be vector OB minus OA. I wouldn't write this down every time, but we'll write it down once, which is negative 3, 8, minus 2, negative 5, which is negative 3 minus 2, 8 minus negative 5, which is negative 5, 13. So negative 3 minus 2 and 8 plus 5. Okay, so at the bottom of your page, you've got the recommended numbers for the work.